And we are back here. It's Wednesday, and we have 8 a.m. here. We have sections 3 and 4. Very good. And we're still in chapter 16, of course. Recitations start tomorrow for all sections 1 through 12. We changed up the TA assignments a little bit, but the names of everybody are on there on Learning Suite, so you can see who your TA is. We have some of our TAs here today. Gannon's over there. I saw Braden. Let's see, was Tyler here too? Tyler's in the back. Yeah, you'll meet these guys. And yeah, it starts tomorrow, so click on that URL. We'll also have the TA Help Room Zoom spreadsheet, which you'll be able to click on and get help many different hours of the day. I'll post that as soon as we have that. Usually it's the second week we'll get that ready for you, so you'll have help available. I had a few people Zoom into office hours yesterday. That's good. I'm available to help too. Let's see, we'll have homework and quizzes starting next week. So you're off the hook here for this week, getting caught up on chapter 16 there. And we went over the syllabus and the schedule and everything. I hope that's clear for you. If you have questions, email me or during my office hours. I can, of course, answer those questions, but everything should be okay that way. Let's go over to the board here to start out today. And we talked about resonance, and we need to review a little bit about that. We've got polyenes now. We need to talk about this resonance stabilization energy and a little bit more maybe on the properties, conformational issue, and a little bit of on MO theory, not much. Those are kind of minor topics. We'll get to the main event, which are the reactions, right? The 1,2 versus 1,4 additions with butadiene, and then the Diels-Alder reaction. Those are the two new reactions. So we're just giving you a little background here. So this should be familiar. Carbocations, primary or the least stable. Okay, so like a methyl cation or an ethyl cation. Those are very unstable. Secondary cations are a little more stable, not much. Okay. They're still not very favored. Tertiary are the good ones, tert-butyl cation. And then here's allyl cation. Even though the two ends you could say are what? Primary, it's about as stable as a tertiary carbocation. And then if we combine the two, remember we had that reaction last time that we covered, that SN1 reaction ionizing, where it's what? It's got this allyl resonance and it's tertiary. You know, if we draw the resonance structure, we get the primary end over here. But that stability of having it delocalized over the three carbon atoms is beneficial to the stability of that. You saw the relative rate and the two different products that resulted from that. So kind of a review there. Let's review some of the types of resonance. So that is allylic resonance that we just showed there. There's other kinds of allylic resonance you may remember, which is acetate itself, okay? From acetic acid. This is the conjugate base from acetic acid. You can see the three atoms here, and that's what? Allylic resonance, right? And so, and that's a beneficial thing. That's why acetic acid's an acid at all, much more acidic than an alcohol, because what? The conjugate base benefits from this allylic type resonance. So that's usually with a charge thing and odd number of atoms involved in the allylic resonance. We can have an intervening alkene and have 5 things there. Conjugated ones, and I think I showed you this one. These are typical neutral things like butadiene, but this has resonance, right? What's the resonance structure here? Well, let's push the electrons over, double-headed arrow, and what's our resulting structure here? Yeah, it is charge separated. You know, that's not a good thing, but that accounts for some of our understanding that what? There's double bond character between C2 and C3 and butadiene. Remember, we had that bond distance thing last time. We need to get into more of that to talk about MO theory, but yeah, this is conjugated systems where you can just push the electrons one way or another and get charge separation. With cyclic ones, again, with an even number of electrons moving around, benzene, we'll see in chapter 17 and 18. And what type of resonance can we do there? Well, just push the electrons around the ring and you can get the other degenerate resonance structure. It's also neutral, but that's a beneficial thing. We'll go into more details on that in coming up chapters. We can have lone pair resonance here, which is another form of stabilization. So say we have a carbocation next door to an ether, and that oxygen, or it could be a nitrogen, it could be an amine next door. This carbocation is secondary, and you could say, well, that's pretty unstable. But it benefits from resonance because of the lone pair, right? So can we draw a resonance structure of that? Yeah. And we see the charge switches over to oxygen. Make sure formal charge, you can calculate that and determine why this has a +1 charge now on oxygen, where the +1 charge was here on carbonite. This lone pair resonance can be a beneficial thing. We'll see that over and over again too, especially with carbocations that have nitrogen next door. So I think you can draw a resonance structure there where you have a nitrogen carbon double bond, and then the charge would be +1 on nitrogen. That's called an iminium ion. That'll be an important intermediate we'll see later on. What do we mean by polar? Well, that's where it's a neutral thing, an even number of atoms. And what? These electrons are distributed in the pi bond between carbon and oxygen for a ketone or carbonyl. But this can resonate, right? We can push the pi electrons up onto the more electronegative atom. Don't do it the other way here. We don't push the electrons down here. Why? Because that would give a plus charge on oxygen there and then a negative charge on carbon. If we draw it this way, we get this, right? And that's a beneficial thing. We can combine these. We can have multiple effects going on here. So something like this. See, if we had a carbocation way out here and then an intervening alkene, we've got the lone pair that can come in and resonate there. And so we're kind of combining what allylic resonance with lone pair resonance. And what would be a structure here? There are a couple different structures actually here. And that would give one like that. But that will help stabilize that intermediate. Anything that's charged like this involving resonance structures, these tend to be intermediates. We don't isolate those typically, but they'll be intermediates. But ones like this, these are neutral ones. The polar example and the conjugated example, these are neutral compounds that benefit because of the delocalized pi electrons. Okay, another quick concept here on polyenes. That would be the conformation. Now, let's look at the conformation here of butadiene. And maybe let's start with just the idea here of a simple alkene. Now, when we had the transalkene here, we think about rotation around a pi bond. Okay. Remember, we said we can't do that. Here's the trans. Can we isomerize over to the stereoisomeric, cis alkene there? Is this normally going on? Is this in equilibrium? Yes or no? What do you guys say? Most people shaking their head. And why is that? We'd have to break this pi resonance here. Anybody remember roughly how much energy that would cost us to do that with a simple alkene? It's about 60 kcals per mole. That's a lot. Thermally, at room temperature, we only have available about 25 kcals per mole. We have to heat that up a lot or shine light on it. In the special case, it was a polyene, like we saw with retinal and opsin, the vision process. We can isomerize from E and Z, but that's a special case, right? Where it's highly conjugated and enzymes are involved and light is being harvested. But a simple alkene like this does not isomerize from cis to trans, okay? It's a big barrier. We got to break that. Well, what about this barrier right here? We saw from the bond length idea last time that it's a short bond relatively, but what is the conformation around that? So we'll have to look at that. If we normalize the energy here, we'll call this 0 kcals right now, okay? And then we're going to isomerize that over to the out of conjugated position here, where we're going to rotate I think about 90 degrees there. I'll show you the models. And this is kind of hard to see at first here. This is kind of coming out at you now. And yeah, these are kind of in a plane here. So we've broken the resonance. With the models, this will make a little more sense. And let's keep going the whole way here, isomerizing over to the cis. Now, we call this the S-cis, and we call this the S-trans. And the S refers to rotation around a sigma bond. Okay, it's not a true full sigma bond, as we'll determine with MO theory too. But we're rotating on a polyene now between the non double bond positions, we can say. Okay, there's more S character here. And what's the magnitude here? Let's see energy-wise. This can be calculated and actually measured quite carefully. This one goes up in energy. If it's out of resonance now, and the models will be a little more clear, that's plus 6.7 kcals. But at room temperature, we have what? We have 25 kcals per mole thermal energy. So it can rotate out of resonance. It is of S character. We're not breaking the pi bonds that are localized. Notice here as we rotate, there's still pi bonds here and here. We're just breaking this conjugation resonance. And it's about 6.7 kcals, which is a lot less than the 60. Okay, that should make some sense. And then we go over to S-cis. Let's see, is this going to be higher or lower than the S-trans? What do you think? Will it be higher or lower than the out of conjugate? It's back into conjugation now, right? But it's now with the S-cis conformation. So is this higher or lower in energy? You have a feel for that? Be a little bit lower than this. They'll probably be higher than this, right? Let's see, what is it? I got the actual number, don't I? Oh, 2.8. 2.8 kcals. And that should make some sense because these two hydrogens now are pointing right at each other, okay? So conformationally, this should kind of remind you of what? Staggered and anti-conformations of alkanes. Remember, we looked at that conformational freedom around sp3 hybridized bonds, okay? And there were those small barriers. Prefers to be staggered, right? Apart from each other. If they're eclipsed, that's about 2.9 kcals per mole, and they go past each other. But at room temperature, that's going really rapidly, okay? There's plenty of energy to do that. With alkenes, we can't rotate here. Why? Because we're breaking the pi bond. If we rotate that, we don't have the pi resonance. But with polyenes now, it's a little bit different deal, right? So let's see. We've got butadiene here, and we have the two pi bonds, and then you see we got the pi character here for this overlap, right? So let's see, this would be the low temperature, most stable conformation, okay? And that's the lowest one. You know, it's S-trans here, but let's rotate out of plane. So that's this guy right here now, okay? And you see, we've broken the resonance between C2 and C3 there. But we still have the pi resonance here, the overlap here at C1, C2, and C3, C4, okay? Make your own models if this is still a little tricky to see. Hopefully this makes a little sense. Well, let's keep rotating over to now we're S-cis here, okay? You see the two hydrogens getting closer together? So that's a steric thing that makes that a little bit higher in energy than the S-trans. But we still have the pi character here, okay? We never broke that between the two end positions. We just rotated between the conjugation. So that's a special thing, okay? Consequence of that. So, you know, don't memorize these numbers, but have a feel for it and relate it to the actual isolated alkene, okay? Let's go to the overheads now. Just you're in. Polyene Hall of Fame. We already showed a couple of these, I think. Maybe we can point this out. So even garlic, here it has a sulfur and a couple of saturated carbons in between the two alkenes. So it would be what type of a polyene? Those would be isolated alkenes, right, in garlic. And then these cyanine dyes, these have different colors depending on how many ethylene units are in between the two indoles here on the side. That's highly conjugated, and these have colors. These drop down into the visible range. Okay, there's a lot of synthetic dye type materials. These are some of the organic LED materials that I mentioned that are in display panels. They have isoprene in plants that's polymerized into rubber, gutta-percha, the rubber tree. We can do that synthetically, of course. We don't have to rely on the plants to do that. But it gets polymerized from the conjugated diene into the isolated polymeric polyene. Okay, so these alkenes are not conjugated anymore. But we got a couple of conjugated polyenes from nature, carotene and lycopene. What color is carotene and where does it come from? The name says it all, I think, right? Carrots from vegetables. A lot of pigments in nature are these highly conjugated polyenes. Carotene absorbing in the blue and the green region, and so it has an orange color. It's always the color it's not absorbing. So the white light from the room or sunlight, whatever, if it absorbs that frequency, you don't see it. And then you see the colors that it's not absorbing, which is kind of cool. And lycopene, what color is that? Little different wavelength, different vegetable too. Anybody know which one it is? Tomato, yeah, it's the red color. Very good. But these are what? Conjugated polyenes. A lot of alkenes conjugated. And then we have squalene, which is a precursor to cholesterol. We'll see that later on. What type of polyene is this then? Just looking at structure. Is it isolated, conjugated, or accumulated? Remember, there's three flavors. Which one is this, squalene? Isolated. Yeah, they're not right next to each other. Same thing with arachidonic acid and lipid bilayer membranes. All right, let's get into this, the dreaded MO description. Now, again, we're just qualitative here. I'm just going to mention enough of it to confuse you and annoy you. No, enough of it to show you how it's useful to help explain the stability and the reactivity of some of these things. So here's all the basics of MO theory boiled down. You should remember some of this. These are linear combinations of atomic orbitals, okay? The wave equation, we can do that mathematically. Psi, if you square psi, that's the probability of where the electrons are found. Remember, orbitals are locations in space to determine where electrons are found. And we draw out the probability to 95%, and that's the artificial drawing we have for the orbitals, okay? Actually, they taper off to infinity. That's kind of a weird thing to think about, but 95% is what we actually draw here. So hydrogen, here's the hydrogen atoms. We can bring them together in phase or out of phase to make the hydrogen molecule. So here's the MOs. If we have two atomic orbitals, we generate two molecular orbitals. Okay, that's one of the paradigms for MO theory. Then it's an array of linear combinations for the actual molecule that go up in energy, depending on how many nodes are present in the linear combinations. If they come together in phase, and what do we mean by phase? These are little small weird particles, right? Quantum mechanics says they have wave-like properties, meaning the two electrons can be in phase or they can be out of phase. And that's all that means by the sign of the wave equation, okay? It's a mathematical description, plus or minus. It's not referring to charge. It's referring to whether it's a peak or a trough in that wave-like propagation of the electrons. So if they're in phase, that's good overlapping in phase, to make a sigma bond, where the electron density is on the axis. That's what sigma means. Sigma star is also there, where they're out of phase, where there's a node between the two. In the ground state, we put the two electrons in the low energy orbital, but that anti-bonding orbital is there. If we electronically excite that, we can decouple the electrons and then weaken that bond, okay? It can decay back down and form the stable ground state structure, but we have a position in space for that electronic excitation. So all of this is talked about here if you want to read through that, but I just summarized it for you, okay? And don't worry about it. You can apply it to ethane. So here's the sigma bond between the two carbons. Here's the sigma star between the two carbons. And we're just looking at the two atomic orbitals from the sp3 hybridized carbons. We're not doing the carbon-hydrogen bonds on the end here of ethane, just the carbon-carbon bond. But notice there's that node there between the two things, and they're out of phase with each other, okay? Now we can do ethylene with the pi bond. We have sp2 hybridization. And we have the sigma bond right here. between the two sp2s pointing at each other in phase, and then the two p atomic orbitals left over. So remember, sp2 hybridization means one p orbital is not changed. It's still with its atomic position there, right? It's a dumbbell shaped thing. It's this guy right here, top and bottom. This one right here is the sp2 orbital. So those come together to form the sigma, and then the two p's come together to form the pi bond, okay? That's the highest occupied molecular orbital in the molecule. We also have the pi star, which is the pi bond out of phase, and then we have the sigma bond out of phase, okay? And what do we mean here? Why do we have 4 here? Because we have 1, 2, 3, 4 atomic orbitals we're looking at. We're not looking at the other carbon-hydrogen bonds. We could do those. It'd make this a lot more complicated. I'm trying to keep it simple for you. But the nodes increase here, you see. This is an anti-bonding orbital. It's unfilled. That's the lowest unoccupied molecular orbital. And then the really high one is the sigma star that's out of phase. Yeah. But yeah, that's the basics of it. Was there a quick question there? Yeah, go ahead. Yeah, so a question about reactivity. Does this make more likely to react? Well, these positions in space then, these antibonding orbitals, show us where the empty orbitals are. If this reacts with an electron-rich species, we could say that nucleophilic figure would come into the pi star. If we react with an electron-deficient species, we would react the electron-rich position in the molecule as a nucleophile. Those would come out. So yeah, these do have to do with reactivity and electronic excitation for the colors, whatever. So let's just strip away everything else and just look at the pi bonds in isolation. So for ethylene here, you know, the models over there, make sure you know a pi bond and pi star, okay? And that's what we're looking at here. In the ground state, the 2 electrons for the pi system. We're not looking at the sigma bond system. That's usually higher in energy. And this is perpendicular to it, by the way. Oftentimes in isolation, we can do the calculations just on the pi system. And that will give us a good depiction of the molecule. So here's the HOMO, here's the LUMO. We say this one's bonding, this one's anti-bonding. So the regular pi, and why do we call it pi? Because the electron density is off the axis. Forms a little sandwich of electron density, above and below, okay? Now if we have 3, allylic system, and we just mentioned allylic, can we apply MO theory for these guys? Yes, we can. Here's the ground state where they're all in phase. And again, we're just looking at the allylic system. I'm not saying anything about charge or about the number of electrons yet. We'll get to that, okay? You'll see how it'll change here. But we're just depicting the phases of the p atomic orbitals that come together to form the pi bonds now, okay? So this is the molecular orbital where it's all in phase. And we have the density below and above. It's a bigger sandwich now, okay? So this is the difference now. Before you thought about MO theory involving just 2 atoms coming together to form a pi or a sigma bond. Can we have MO theory apply to bigger systems with multiple atoms? And the answer is yes, and all the principles apply. So this is just a bigger pi bond where they're all in phase, a bigger sandwich, you can say. This is like a hoagie or a submarine sandwich now, instead of your little Oreo cookie for your single pi bond. But they're all in phase there. That's psi 1. If there's one node now, okay, and that's the deal, MO theory, as you go up in energy, you increase the number of nodes that are present. So here we have to put the node right at that atom. So the electron density actually drops to 0 at that middle atom. That seems kind of weird. The electron density is found on these 2 atoms on the side because that's where you have the one node. You see it's out of phase there. We call that a non-bonding position, but that's okay. If we go up here and have 2 nodes now arrayed there, everything's out of phase. That's the even higher energy one. Depends on which is which here. For allyl cation, we only have 2 electrons in the system, right? We have a cation on each side, okay? But those 2 electrons are spin paired. The electronic depiction, the phases, is they're both in phase, oscillating up and down over the whole 3 atoms, okay? This would be the antibonding orbital. Okay, it's empty right now. That's the LUMO. This is the HOMO for allyl cation. If we have allyl radical, where we've got, a dot, one carbon, one electron on one side or the other, that's a total of 3 electrons. We have an unpaired single electron there, singly occupied. That's what the radical looks like. There's 1 electron in this oscillating mode, okay? That's different than the allyl cation, right? And then the allyl anion would have 2 electrons on the end with a negative charge, right? And that, we'd have to put those 2 electrons here, spin paired, in this orbital, okay? That would become the highest occupied molecular orbital for allyl anion. And then the antibonding one would be over here. And everything I've just depicted or shown you there is what we know about the structures of these 3 different species, okay? But it relates to MO theory over what? 3 atoms now. Can we do it over 4? Yes, we can. And we'll go back to the model here in a second, but if they're all in phase in the ground state, there's that pi character, right, between C2 and C3. It does have pi bond character. There is hindered rotation. Breaking that resonance is about 6.7 kcals per mole to break this resonance right here, okay? Because butadiene has this molecular orbital filled in a low state where they're in phase. The next array up would have 1 node here, but notice on the 2 sides here, these are still in phase. So these are still bonding over here on the ends. This is out of phase right there. But that's our HOMO. We have to add the 2 more electrons there for the 4 pi electrons, right? There's our single bond character. That's why we can rotate around it, right? So the different orbitals kind of manifest different electronic character that you're already familiar with. But now we have 4 atoms and 4 electrons. It's a little bit different, but not much, okay? And then the next higher orbital has 2 nodes. But yeah, look, we're back to pi character between 2 and 3 there. And then the highest one, very high in energy, they're all out of phase with each other. This is reminiscent of standing waves. If you're a musician, play a guitar, whatever, violin, the string can oscillate like this, the primary harmonic, right? Or it can oscillate off of each other and have a node, no displacement right in the middle. That's the octave up, right? In fact, you just touch your finger there and it sounds the octave up. Or you have the next harmonic, the next octave up, if you touch the 5th position on the string, okay, you have that oscillation going on, and the real high energy one is that. You can do it with a rope too, or a string, jump rope. You can do the same type of manifestation for these energy. Anyway, questions on this real quick. So just the basics of it. Let's look at the model here again. So yeah, where they're all in phase like that, that would be that lowest energy MO, right? The next one up be like this. And I switched it over to the S-cis. Don't worry about that. You can just reassign those phases there. But notice we're still in phase on the 2 sides there. We're out of phase right in the middle there. And then how would we go to the next one up? That would look like this, right? So now we're in phase here in the middle, but out of phase here and here. So we got 2 nodes there. And can we do the one with 3 nodes? Yeah, 1, 2, 3 right there. Okay, so that'd be the highest one up. Okay. Anyway, yeah, so it's molecular orbital theory, the combination of those being important. One quick thing here on also figuring out this conjugated diene stability versus isolated diene. So you see it right here. Here's the conjugated one, the isolated one. If we do the heat of hydrogenation, we can measure this accurately. We get about 30 kcals per mole for each isolated alkene being hydrogenated there with hydrogen and palladium. You can measure those energies carefully. If they're conjugated, it gives off less heat, okay? And why is that? Well, this starts out at this more stable position, right? This resonance overlap here is worth about, if you do the reaction measurement, it's about 4 kcals per mole, okay? And this comparison's a little bit difficult here because this is a disubstituted alkene versus a monosubstituted alkene. Remember, the more substituted alkenes are more stable to begin with, so this gives off less heat too. Right here's the experiment where the difference in the heat given off, this delta G, and blue there is this resonance stabilization energy, okay, between the conjugated position. So again, don't memorize those numbers, just have a feel for it. Yeah, conjugation means it's going to be more stable. And remember your alkene stability. This is back to 351, the Zaitsev's rule. We always form the more substitute alkene if we do an elimination or dehydration reaction. So this is comparing the isomers of C6H12. So these are all what? Stereoisomers or constitutional isomers of that. And you see the tetrasubstitute alkene is the most stable one. That'll give off the least amount of heat when in reaction. The monosubstitute linear alkene gives off most heat because it's the least stable, okay? The least stable ones are higher energy. So it's kind of a combination of those things. Let's go to the board here and get to the main event, which is the reactions now. So let's get into 1,4 versus 1,2 additions. And we'll start out with symmetric dienes, and then we'll get to the ones where 1,2 and 1,4 give us different products. First one we'll look at is taking cyclopentadiene and reacting it with one equivalent of HCl. So what is our product here? Well, it's this. Not this. And the question we can ask is why? Okay. So we're doing hydrohalogenation, just like 351. We're adding what? An HCl here. And we're breaking the carbon or the chlorine hydrogen bond. And we're not putting HCl in water. There's no water in there. And we're bubbling the gas in there. And actually, HCl on its own is a covalent compound. We put it in contact with an alkene, and it'll react this way. We're pushing electrons to the more electronegative thing. But the question is, where do we put the proton, the H plus, right? And that's what that is. We're protonating the diene. Are we protonating the diene on the end, or do we protonate the diene on an internal carbon? It's symmetric. Either end's the same. So let's see vote-wise. Should we protonate on the end here, or should we protonate in the middle? Who says we should protonate on the end? Raise of hand. Okay, who says we should protonate in the middle? Okay, a few brave people. Let's see, let's protonate on the end here. And if we do that, what do we get? Okay, again, that's protonating here on the end. Let's protonate on the middle. What do we get here? Okay, changes, doesn't it? Okay. Now, maybe let's re-vote. Who says we should protonate on the end here? Okay, maybe a couple more. Who says we should protonate in the middle? No one? Oh, come on. Why did you guys bail out on the middle? Who can tell us? Why is it favorable to protonate here on the end of a diene? Yeah.
Because it gives you resonance with the...
Very good. You can see the intermediate here. Okay, we're going to draw a resonance structure, right? And it's symmetric, right? And that's going to be favorable here. We're going to have this resonance going on now. We have an allyl cation if we protonate on the end. So that's your key idea there. Make sure you protonate on the end to start to think about these things. You can see, and then our product is just generated when chloride attacks on either side. This is symmetric, and we give the allyl chloride product. We do not give the non-allylic chloride. You see, this is moved over a position, right? That would be the chloride attacking here. Okay? But we're benefiting by at least 10 to 12 kcals per mole energy, more stable protonating on the end, okay? That's going to be favorable. This is very minor. We're not going to have you put that on a quiz or a test. Just put the major thing. There is a tiny amount of that that's formed, okay? But the major pathway is the one that has the allylic resonance there. All right, let's look at butadiene. Now, butadiene, you could say, is even simpler than cyclopentadiene. But butadiene is going to have two different positions. The allyl cation is not going to be symmetric on the two ends. Okay, let's do this. So HBr and HCl are the ones that we're going to do here. HF is not acidic enough to have good reactivity. HI, hydroiodic acid, is too acidic, very corrosive. We don't normally use that for practical purposes. HCl and HBr are the ones you need to know with different dienes. And we'll stick with conjugated 1,3 dienes, okay? And what do we get here? Well, if we do this at minus 78 degrees, you can do that in a cold bath, no problem. We're gonna get this product here, 81%. And we're also gonna get this guy, 19%. They're both allylic bromides, okay? And they're both gonna come about from protonation on the end position, but at low temperature, oh, I need an alkene there. We call this the 1,2 product. We call this the 1,4 product. And that's the position of the protonation relative to where the nucleophile comes in at. And that's low temperature. We call that the kinetic process because the 1,2 is typically faster position-wise to do it. Now the question is why? What's going on here? Well, we know how we can start out, right? We can start out by protonating on the end, just like we did before. And what do we get? We get this, okay, which is our allylic cation. And you could say, well, if it's at this secondary position, yeah, we can see that bromide attacking there is just going to go to the 1,2 product, okay? So far, so good, but why should it attack there? Okay, let's see. We can resonate this intermediate double-headed arrow, right? What will the resonance structure look like? It'll be over here. Now, what's the difference between those two? Well, they're not the same. Before the allylic cation and the cyclopentadiene, that was symmetric. But now with butadiene, notice the two ends are different, right? This is really a localized secondary cation. This is what? This is a primary position, okay? We can draw the composite of this, and oftentimes you'll see this with the dash thing over both ends. But notice the two ends are different, okay, if we consider the localized structure. The true structure is this, where, you know, these are all in phase. The low energy molecular orbital, they're all in phase. And the two electrons involved there in that orbital oscillating up and down, if you want to view it that way, over these three atoms. But we got different reactivity now. And so what do we do here? Bromide, we can get, you know, going on here to rationalize the 1,2. And the 1,4 is easily rationalized here. But why? The question becomes why? At low temperature, what are we talking about? Well, you could say this would be the more stable cation, right? Being more substituted. And that's okay. More of the plus charge, more of the lack of electron density is going to be at this more substituted position. And that's, you know, carbocation stability, right? That we summarized before. The more substitute carbocations are more stabilized. Why? There's two factors there. Inductive donation of the adjacent carbons, and then hyperconjugation. We can review those if you'd like, but I think we're okay on carbocation stability. You can see this would be the more stabilized, localized carbocation. And you might say, well, that's where most of the nucleophile will attack then at low temperature, okay? And that makes some sense. This one's primary, so that's not going to be as important at low temperature to give this product. So this is the minor product. You can just show this one as the major one and get full credit. You can ignore the minor one. At low temperature, though, that's the key right there, okay? Well, let's do another experiment here. Let's do this same experiment now. Same thing, HBr, but we're going to do it at, let me see, I've got the numbers here for room temperature 25 degrees C. Same thing here, and we're going to get out, let's see, what is it? 44% 1,2, and we're going to get out 56% 1,4. Look at this. Higher temperature, we're starting to get more of the 1,4. Okay, let's see if we see a trend here. Let's do what? Let's see. I've got it. Yeah, 50 degrees. Everything the same. Now we're just going up to 50 degrees. And that's kind of what we'll do in the class. We'll keep minus 78 or minus 80 degrees versus 50 degrees. Okay. What do you think here? 50 degrees, we get 15%. It almost switches completely. 85% now. 1,4. And we're going to call this 1,4 product because it is the higher temperature. What are we going to call that? The low temperature we call the kinetic product. Anybody remember from the reading what we call the higher temperature? Thermodynamic product. Yeah, this is our thermo product. And again, the question is why, right? What's going on here? Let's see. So we can say kinetically, this 1,2 is forming faster. That's where more of the substitute carbocation is. But what's so stable about 1,4? If we have higher temperature, we're getting more of that. In fact, it become the dominant, probably the major one. If that's the only one you show, make sure you're linking that to the higher temperature, okay? But what's going on here? Yeah, question. Okay, so someone says if you got higher energy, higher temperature, you can break a bond and go back. Maybe it's reversible at higher temperature and then give you the more stable. This over here is the more stable, more substitute alkene. Okay, more substitute alkene. That's kind of the key idea there, right? Before at low temperature, it's the more substituted carbocation where more of the positive charges, and that's a faster addition. But at a higher temperature, we're going to break a bond, reverse it, and go and form the more substitute alkene. Because look at the 1,4 product. This is disubstitute alkene versus the 1,2. We're giving a monosubstitute alkene. Let's see if we can draw an energy diagram here and begin to make some sense. So high temperature, I'll write that over here. So 50 degrees, see, this is major, okay? And that's thermo. So let's draw the energy diagram here and see if we can make sense of this whole thing, okay? So here we have our alkyne, HBr, and we're going to protonate it, go to our alcation, okay? And then at low temperature, we're going to go down to our 1,2 product, okay? So far so good. You know, the protonation, this is higher in energy. It's cation there. Very protonate, and yeah, we go down to a lower energy point than the starting material. And yeah, that's a favorable thing there. But notice we also have the ability to go down here to this product. And I think this diagram helps us see what's going on here. But this barrier right here is the kinetic one. So at low temperature, this is going to be faster, okay? You see that barrier there? And that's where more of the positive charge is at that secondary position. So that's why the attack of the nucleophile is going to be faster there to give that kinetic product. But notice I'm drawing these different in energy right here, right? And what's the difference here? Well, that's the alkene stability. Disubstitute alkene versus a monosubstitute alkene. This one's forming faster kinetically, but as was pointed out, if we have more what? Energy, more heat, this can reverse back. We can break this off. So this becomes reversible at high T. Sorry if my drawing's going to get kind of messy now. That's just what was stated there. So if we got a higher temperature, even though this is happening faster, we can break this bond, go back to this intermediate, and breach this barrier. Okay, this is the slower kinetic barrier, but it leads to what? The thermodynamic product. Here the product is more stable. Okay. So this is thermo, this is kinetic, and this diagram kind of points out the whole shebang, I think. And the key idea is low temperature, you're just breaching this barrier selectively. High temperature, you're able to reverse this back and find a pathway that leads to more stable product. Okay. And that's a hallmark of thermodynamic process. At higher temperatures, you're forming a more stable ground state structure. Okay. Kinetic product here. This also has important implications for enzymatic reactions in biology, where an enzyme will stabilize a pathway that will lead oftentimes to a less stable final product. But it's providing a pathway that kinetically is faster than other pathways that might lead to more stable products. So it's kind of a counterintuitive idea. A lot of times we've just thought of one pathway leading to one product, but it's different than that, okay? So let's look at some other examples and see if we can figure these out. Let's see this example here. 1,2 versus 1,4. Okay, let's get this one up here. How about this one? And let's do it at minus 80 degrees. Come up with a product and rationalize what's going on. Now we have two different ends. I will tell you it's going to be better to protonate this end here. If you protonate this end, you'll get a secondary carbocation and a primary for your allyl resin. If you protonate this end, you'll get tertiary and primary. Okay. So let's see what the intermediate looks like. Looks like this, tertiary and primary. I'll just kind of label them there. At low temperature, which is going to be attacked, the primary or the tertiary position? Who says tertiary? Yep. Okay. So your product will be what? That right there. And that's formed in 90% yield after you isolate it. Yeah, there is a tiny amount of other things formed, but notice that's the pathway to go. Don't protonate over here on this end, even though that is allylic. Look, now it's secondary primary. Okay. The first thing to do with these more complicated examples of 1,4,1,2 is to consider protonation of either end. You always protonate the end that will give you the most stable carbocations. Okay. Tertiary primary is better here. What if we do the same thing here? HCl at 25 degrees. Well, then we're going to get this product, which is going to have what? The double bond. Now trisubstitute alkene, and we're going to do the 1,4 product. We're at higher temperature here, and the yield here is 85% once you distill that. Okay. So there's another example of it. The 1,2 product and the 1,4 product there. Now, you have to consider, a couple different aspects of this when you work these problems. Let's see another problem here where we've got a little variation. How about this one? We've got cyclopentene there with an alkene on the end. Let me get this data up here first. And we're going to do this at low temperature. 78. See what you can come up with. Question, yes? The 1,4 product is always the more substituted alkene product. Then. Yeah. Thermodynamic, we're referring to the alkene substitution. Kinetic, we're always referring to which carbocation's attacked. Okay. I know that kind of seems weird to keep that straight. But this one here, so what would we do here? Where would we protonate here? We'd want to protonate on the end here because that would be tertiary secondary. If we protonate here on the end, we'll get secondary primary. So kind of experiment with this one, protonate on the two ends and see what's going on there. But our product here will be this. Okay. And that's isolated in 87% yield. If we do everything the same, HCl at 50 degrees, For this example, we get this product. You notice it's the same protonation position, right? Same one when we do 1,4 versus 1,2. But now we're getting the chloride at this position. Why? Because this is tri-substituted alkene, whereas this is a di-substituted alkene. Okay? So we get a high yield of this one at higher temperature, high yield of that one at low temperature. Okay, and yeah, we're out of time. I'll give you another example next time. And next time we'll also be starting the Diels-Alder reaction. Okay, the Diels-Alder reaction, I'll warn you now, is much more synthetically useful, preparatively important. So the Diels-Alder reaction will be, I think, more of an important topic than this 1,2 versus 1,4 diene additions. But very good. Thanks for coming today, and we'll see you next time. All right.